Okay, now let's look at some guidelines for setting pickup relays for phase fault relays. So pickup current should be above the maximum load current, that is understood, because as I said, phase relays are working on positive sequence current, normal load current is also a positive sequence current, so it should pick up above that. Pickup current should be below minimum fault current, that is also your expectation because you want to no fault should go unprotected. Pickup current should also be below the minimum fault current of the feeder that it has to back up, otherwise backup responsibility will not be handled correctly. And the backup relay also should provide time for primary relay to operate. This time interval is known as coordination time interval. I have already mentioned it. So if you are not able to achieve it, I am not saying that because I have put up a slide you can achieve it. If you are not able to achieve it, then overcurrent protection is not the philosophy to be used. Then you may have to use, as I said, the standard mantra I would keep on saying is go for current differential. If you go for current differential, most of the problems will anyway go. But it has an additional cost, communication and so on. So that is where your judgment, your budgets, all that kind of thing comes into picture. But if these things you are able to manage, then you if these things are satisfied, then you have with overcurrent protection a very cheap protection philosophy which is meeting your requirements. Is that clear? So you should not therefore say that because I had put up a slide and tomorrow if you work on a system and that doesn't meet, you should not say your system has a problem and neither my slides have a problem. You have to change your protection philosophy a bit. Now, okay, so supposing that you are going to do overcurrent protection all along, this is how we will do it. This is a single source system. Typically plain overcurrent systems, overcurrent protection will be used for single source radial systems, not even multiple source radial systems. And you start with the leaf nodes here, because these have no coordination constraints. At the leaf nodes there are no coordination constraints. So there is a feeder here in principle. I am just showing the relay location here. This relay does not require any coordination with any other relay, so it should be set first. Pickup current, there are two issues to be decided in setting. One is pickup current, which is anyway, you will do a fault studies and find out what are the fault currents, primary backup, what are the fault currents for the primary section, what are the fault currents for the backup section. Then as I said earlier, your pickup current has to be such that it gives you both primary and backup, and then you will set up the pickup current. So that pickup current setting does not require this graph or whatever. This graph is only to do the time multiplier or the TDS or TMS setting. So to do the TMS setting, you will do it first at the leaf nodes, because these relays don't have to coordinate with any other relays. Therefore their time multiplier setting can be set to minimum, because protection should always be as fast as it can be. Then you go to the relays, look at the relays which are backing them up. So the parent ones, as I call it here in this figure. Then you slow these relays down by the coordination time interval. And then you go back further. So then this is the relays, with these relays will be set next. These first leaf nodes, then these relays, then the relays which are backing them, then the relays which are backing up, until you reach the source. So you start from the leaf node and do coordination and try to reach the source node. So for example, this is so in this system, for example, these are the relays which you will set first: R1, R2, R1, R2, R3, R4, R5. These are the relays which you will set first. There is nothing, they have only primary protection responsibility. They don't have any backup responsibility. Then you go and set the relays which are backing them up. So these are the red relays which are backing them up. So these are the next set of relays which you set up. Then the backup relays become the primary relays. The backup relays become the primary relays in some sense, and then the next these relays are to be set up. So if you look here, let's carefully identify. First you have set R1, R2, R4, R5. You can just write down just to keep a track of it. R1, R2, R4, R5, R3, R4 and R5. These are the 5 relays which you set first. Then identified relays, backup relays are R6, R7, R10, R8 and R9. So these are the identified backup relays. Then in the next set, we are setting up pardon me, 1 minute, what happened? Yeah, the blue relays is what we are setting up. R6, R7, R8 and R9. So the R10 is not yet set. We have set R6, this backs up this has to back up this. So these relays are set and these relays are the backing up relays. What am I doing? Yeah, then this is set, this is set and then this is set. Okay. So see these relays, let me put it this way. This is okay. This is also okay. I'm just thinking about why I have not put the R10 here in. See, let's look at it. Let's not look at the animation, so to say. First we will set R1, R2. Let me just look at it. First I will set R1, R2, R3, R4, R5. That's the first set of relays that I will set. Once I have set these relays, then I will set which relays? After that I can set R6, R7, R10, R8 and R9. Okay. Then after that I will set, have I set R6 and R7? Yes. If I have set R6 and R7, then I can set R13. In the step 3 I will set R13. In the step 1 this relay, in the step 2 this relay, and since this relay is being set in the step 3, this relay cannot be set now. You get the point? See, these relays are step 1 relays, then the step 2 relays are those which are backing the relays set in the step 1. So 1, 2, 3, 4 and 5, these are the next set of relays which you will set. Then after that you would set, yeah, so these are the red relays which are set first, then these are the primary relays. Okay, then these relays are set second. I think that is also correct. Then these relays are, this has already been set, that's why it's not been shown. Okay, so the red relays are the relays which I am showing, the blue relays are the corresponding back relays for which the backup action has to be provided. Then I am setting these 3 relays. This relay has already been set. Then I set these 2 relays, they back up here, and then I set this relay, they back up here. So is this clear? I mean, I think it's pretty clear now. I mean, I was myself. Red indicates the relays which are being set. So these 5 relays are set first. Then the relays which are backing them are set. You clearly show that these are the relays which you are backing them. These are the relays which are set now. Short circuit current will be different. Yes. I will take an example of relay coordination. Right now we are just seeing the sequence. Then this set of red relays are set. Then this set of red relays are set. Then this set of red relays are set. So the sequence of setting, basically the sequence of setting is such that you are only ascertaining that the relays which they are backing up have been set beforehand. You cannot set a relay X relay, if X relay backs up a relay Y, then unless the Y's time multiplier setting has been decided, you cannot decide the time multiplier setting of relay X. X backs up Y. So Y's time multiplier setting has to be first decided. Once only it is known, then you can decide the time multiplier setting of relay X. That is the only way in which you go about and do this sequence of coordination. Okay. So the same thing is mentioned here, so we will take one example now. So PSM settings for primary backup protection, setting of relays, fault type, city burden, primary pickup. Okay, this is the example problem. So what do you see in this example problem? You see that this is a radial kind of a system. R1, R2, R3, R4 has to be set. Our guideline is pickup current should be above 1.25 times the maximum load current. Pickup current should be limited to 2/3 of the minimum fault current, so that you will always get a PSM which is greater than or equal to 1.5. So you don't have to worry whether you are working with numerical or electromechanical relays and so on. As I said, PSM of electric mechanical relays should not fall below 1.5 value, because the manufacturer does not guarantee you the operating time below that region, even though it's shown on the curve. And the backup protection is provided by time discrimination principle. So for this system, this is the maximum fault current feeder, maximum feeder segment load current, MXFL, full load current maximum value. Okay, so relay R1 sees a maximum load current of 50 amperes. Relay R2 sees a maximum load current of 100 amperes. 50 plus 50 will flow through this 100. This one will see maximum for load current of 200 amperes and 250 amperes. So 50, 100, 200, 250. This is the maximum load current which you are going to, which this relay is going to see. See, load current varies over a day. So I am talking of maximum load current which this relay is going to see. Then, as I said, the pickup current, the phase, we are not setting right now the earth fault relays, we are setting the phase relays. So the pickup of the phase relay should be at least 1.2 times the maximum load current, so that it never operates on a load current. So therefore pickup is set to 62.5, 125, 250, 312.5, that is 250 times 1.25. 200 times 1.25 and so on. Then the minimum fault current, this you will get from a fault studies, is 250 amperes for R1 and 650 and so on. These are the minimum fault currents on the primary section that you are on that particular primary section of the feeder. So relay R1, it has no backup responsibility. Its minimum fault current is 250 amperes. So I said pickup current should be less than 2/3 of this. So therefore the upper ceiling on the pickup current comes out to be 2/3 of 250, which is 167 centimeters, 167 amperes. So that means there is a range of pickup from 62 for setting R1. You have a nice range of, big range of deciding the pickup current in this example, which is from 62.5 amperes to 167 amperes. So, and the maximum fault current is 500. So you don't have to worry about that. Maximum fault current is always above the minimum fault current. So right now don't have to worry about it. So let us say that we decide, here we have a lot of choice. Suppose we decide that we will set the pickup current to 160 amperes. So we will, in this case I have decided that the pickup current should be, it should be pickup current, I think. The pickup current is 160 amperes. It's not the PSM, the pickup current is 160 amperes. And make the time multiplier setting as low as possible for this particular relay. The time multiplier setting, the R1 has no coordination responsibility, so its time multiplier setting should be as low as possible. In this case we have chosen R2. Now relay R2 sees the load current of 100, so its minimum pickup current should be 125 amperes. And what is the minimum fault current that it sees? Minimum fault current that it sees is, actually when we are deciding the setting of the relay, it is the same 250. On the primary section it is seeing minimum fault current of 650 and maximum fault current of 1200. That is on this particular section BC, it sees 600, 1200, whatever. But this relay has to back up all the way up to A. This relay has to do not only provide primary protection here and provide backup protection all the way up to point A. And since therefore you have to look at the minimum fault current seen by the relay R1 which it is backing up for setting purpose, and that current is and that current is 250 only. So therefore the maximum pickup current is 250 into 2 by 3, which is 167 amperes only. So the minimum pickup is still 167, maximum pickup current is still 167, and minimum pickup is 125. So the range is now reducing between the pickup, and the pickup range has reduced a bit. Since we have set this at 167, we choose 167 as the PSM value. Any number in that range can be chosen. I mean, to keep my life simple, I have seen that sort of tried to keep both these pickup values nearly close, so that I can play with TMS. For illustration's sake, I can give you a better illustration. Okay, so I choose 167. Now, how did I get this 0.07? We need to work out. That is the next step that we will work out. Now, first we will finish up with the PSM step. Now, relay R3 sees 200 amperes current. So, minimum pickup, which is 1.25 of it, will be 250 amperes, and the minimum fault current on its primary feeder is 1100. But the maximum pickup is not 2/3 of 1100 again. It is 2/3 of 650 amperes. Why 2/3 of 650 amperes? Because this R3 is backing up R2, and the minimum fault current seen by R2 on its primary section is 650 amperes. So that current has to be protected. This has to back up this section, not this particular, for this section. Back up the next section, and therefore it should detect a fault current of 650 amperes. Therefore 2/3 of 650, which is 433 amperes. So therefore the range is 250 to 433. I have maximum fault current is 2000. We have decided that we will try a pickup value of 400 amperes. And similarly for R4, let me not repeat that calculation. 250 into 1.25 is 312.5, and minimum fault current for its own section is 600, but backup ke liye minimum fault current is 1100. So 1100 into 2 by 3, which is 733. So therefore the maximum pickup current can be 733, minimum pickup current can be 312. So we have chosen a number on the 700 side, and then that gives you, we will see the TMS values how we calculate. So after this slide, basically the pickup currents have been calculated now. So we have calculated now the pickup currents. Now we have to find out how do we calculate the time multiplier setting values. So to calculate the time multiplier setting values, let's look at this. First of all, if you notice the way overcurrent characteristics are there, they come closer towards when the fault currents are high, they tend to come closer, and when the PSM is low, they tend to diverge a bit. So they are not exactly running parallel to each other. When you increase the TSM, you don't see that they are running exactly parallel to each other. They tend to converge when you on the higher fault currents, that is the PSM is high, and they tend to automatically diverge when the PSM is low. So that means the coordination should be done on the higher fault current sides. When you do coordination on the higher current sides, automatically, because they diverge, the backup relay characteristic tends to go further away from the primary relay characteristic as the fault current reduces. So therefore it automatically gives you coordination on the lower current side. So the coordination job is done on the higher current side. So in this particular case, so when I want to find out, see, R1 TMS setting of R1 will be kept as small as possible, right? The TMS setting of R1 will be kept as small as possible. Now to decide TMS setting of R2, the fault can be anywhere on the section AB. I have to decide some value at which I will do the coordination. So I will look at what is the maximum fault current that the relay R1 can see, and that maximum fault current is 500. So therefore I am going to do coordination with R1 current. To coordinate R2 with R1, I am going to choose the maximum fault current which is seen by R1, which is 500 amperes. And then at that point I will find out what is the relay operating time here. So the R1 operating time I find out. To that I add 0.3 seconds, which is the coordination time interval, and that becomes the operating time for the relay R2. So now I know what is the minimum operating time of the relay R2. It can be slower than this, but I don't want to make it any further slow. Why unnecessarily slow down the protection system? So therefore I say that I have determined the operating time of the relay R2. Now relay R2, you have seen the standard equations, IEC equations or the ANSI equations. Once you have picked up the characteristic, you know the equation. You know left hand side is T, the operating time of the relay. That value you know. Pickup value you know. Once you know both these values, you can, I mean there is only one unknown which is TMS. So you will calculate the TMS value. I think maybe I should, yeah. What I am saying is you know what is the relay operating time from that graph. You know the pickup value. So once you know this, the only unknown is TMS. So you solve this equation and calculate the TMS value. That's all I am saying. Is that clear? I mean I found from here I found out, adding this operating time 0.3, I found out what is the left hand side. That is the time for the relay to operate. So this time for the relay to operate is now known. The pickup value has been calculated here. This is not the PSM, this is actually the pickup value. The pickup value has been already calculated here. So you know the pickup value, which is IS, you know the operating time of the relay. There is only one unknown, so you just solve that equation and calculate the TMS value. Once you have calculated the TMS value, you can draw the full curve of that relay, because by varying the fault current range, you can get the full operating time of the relay. So therefore, what you do? Oops. So this was the operating time of the relay 1 at 500 amperes. R2 backs up, so you add 0.3 seconds. So you locate the point for the relay R2 to operating time at this current. You know its pickup value, so you calculate the TMS, which is 0.07 from that equation, and then plot that characteristic of that relay. So that's just is that clear? Very simple. Then I have got the TMS value of this particular relay. Now I will see what is the maximum to coordinate R3. I will see what is the maximum fault current seen by R2, because I said the characteristics tend to diverge or whatever. So the maximum fault current which is seen by R2 is 1200 amperes, and with that 1200 amperes I will find out first what is the R2's equation is known, TMS setting is known, PSM is known. So once you tell me 1200 amperes is the maximum fault current it carries, I will find out what is the operating time of that relay by just plugging that. I know the pickup current, I know the TMS, so I will just calculate what is the operating time of that particular relay. Then that locates this particular point here, that on its maximum fault current how fast this relay is. Now the R3 relay, which has to back up, has to work 0.3 times plus has to be slowed down by a 0.3 seconds. So therefore I will find out, I will locate this point D. Once I have located this point D, for this relay I know what is the left hand side, I know what is the pickup value, so I solve that equation, find out the TMS, and then I put this particular curve in its place, and so on I do for the last relay, and I have done a complete relay coordination. So this is the way you do a overcurrent, this is the way you do a overcurrent relay coordination. Okay, just some small point here, that CTs in a legacy thing will, for a phase fault, will see RS plus RL plus ZR as the relay impedance, but in a legacy system, that means where you have 3 phase relays, 1 earth fault relay and so on. For a earth fault, the lead wire current will flow back through the lead wire, because with a phase relay it's only up to the IA plus IB plus IC becomes 0. So after that nothing flows through the ground wire back in some sense. There is no return circuit required. But this requires a return circuit for earth fault. So therefore the CT sees different impedances when there is a earth fault and there is a phase fault in a legacy system. And the earth fault system sees more impedance than the phase fault systems. There are further issues of star delta connections and so on, but I am not going into details of that. Okay, there are some problems which are solved in the tutorial, so you can just work through those solved examples. I won't go through those example. I mean, in the web course you will see that there are some examples which are there. So now let us look at the earth fault protection. So we have done the phase fault protection is complete. We will now see the earth fault protection. Okay. So single line to ground fault involves ground. This is the standard equation which all of you have learned, 3E divided by positive sequence plus negative sequence plus zero sequence, this thing. Yeah, so usually with a feeder section, see what happens, positive sequence and negative sequence for a non-rotating device I have discussed earlier is same, positive and negative sequence impedance is same. With zero sequence there are certain issues. With a feeder, the zero sequence impedance may be 3 to 5 times the positive sequence impedance of our transmission line. So that means if the fault is earth fault is there on basically a transmission system, then the earth fault current may tend to be maybe lower than the, even with a bolted fault, the earth fault current would be lower than the phase fault, because if you just imagine, because Z0 is much higher than the ZS1 and ZS2, so therefore the earth fault, see if ZS1 is equal to ZS2 is equal to Z0, then the current that you are getting there is even by ZS1. So you take that as the reference, that all of them were same, then there is not much difference between the bolted phase fault and the bolted earth fault. If all the positive, negative and zero sequence are same, there is not much difference in the bolted phase fault current and bolted earth fault. But what happens, zero sequence impedance is different from the positive and the negative sequence impedance. For a transmission line it is 3 to 5 times. So therefore a bolted earth fault on a transmission line is usually lower than the bolted three-phase fault. But if the fault is close to a generator, that is utility system, if the fault is close to a generator terminal, then we have seen that for a generator the zero sequence impedance is much lower than the positive and the negative sequence impedance. So in that case Z0, Z1 plus Z2 plus Z0 is less than 3ZS1, that is the 3 times the positive sequence impedance, it's less than that. So therefore 3E divided by something which is less than 3 times the positive sequence impedance means larger. So that means if you are close to a generator, the earth fault current can be higher than the bolted or a phase fault current. And to reduce it, to bring that magnitude within a reasonable range, you can use a grounding impedance. So the generator can be grounded through a certain impedance. If that current tends to be very large, then you would need a grounding impedance Zn, so that this fault current is reduced. So that is how. So it's not like that. For a long time I used to think that the three-phase fault currents are always higher than the ground fault currents, but it's not really true. Ground fault currents can be higher than the three-phase fault currents, especially if you are close to the source. But if you are far away from the source, then the three-phase bolted fault is a more severe fault than the ground fault. And it also depends upon what ground impedance you have provided. And if you became very very safety cautious, or said no, we don't want any high ground fault currents and so on, will increase the ground fault resistance, then what would happen if you make Zn very large? The ground fault current will reduce so much that your relay will not properly detect it. The ground fault will persist, and over a period of time it will create much more, relay will not pick up, and it will create much more damage to the system. Even I have heard of these stories that in the very rocky terrain, the ground impedance is, the earth return has such a large impedance that the ground relay does not operate, and people see some kind of a volcanic pool coming there, and they think some volcano is coming, but it's actually just that the conductor has broken down to the ground. Fault current is not very high, heating takes place, and some melting takes place, which is wrongly interpreted as as you know, some another natural occurrence which it is not. So point is that it's not, I mean, while we don't want fault currents to be abnormally something which we cannot handle and makes the device, the fault currents, earth fault currents, if they reduce too much also, we have a problem in coordination as well as detection. So the Zn is not just something, I mean, otherwise you just open circuit it, no, I mean, why ground generator, don't ground it itself, you will get zero fault current. So your ungrounded system, the first fault which strikes, ground fault which strikes will not cause any current to flow. There is absolutely nothing wrong with your electrical engineering. Yes, the first ground fault will not cause any ground current to flow, but it will develop abnormal voltages. And then the next ground fault or whatever comes is fatal. So it's not, that's why you don't want ground impedances to be very large. You have to choose your ground impedances also when you ground something through an impedance. If you just ground it, solid ground, fault currents may be abnormally high for your convenience or whatever, you may feel uncomfortable with the high fault current. So you will put a ground impedance to reduce it, but you should not try to reduce it so much then that your abnormal voltages problem becomes. So ungrounded systems are not good. I mean, they have an advantage that the first one does not do you any harm in sense of interruption, but the second one is extremely dangerous. It's just, there is a fault and it's undetected, it's not a good thing. Okay, so a rule of thumb is that 5 to 10% is an unbalanced current in a system. So as I said, as earth fault relay picks up on zero sequence. So if 100 amperes is the full load current, and if you take the system is having an unbalance of 5 to 10%, then the earth fault relay will pick up current should be above 10 amperes. It cannot be below 10 amperes. I mean, if you put it below 10 amperes, then it will start operating on system unbalance which you don't want it to operate. So there is a lower side which is a pickup current which is 5 to 10 amperes. So 100 amperes if it is the load current, phase relay is picking up at 125 amperes. So phase fault you cannot detect below, I mean minimum pickup itself is 125. So phase fault you cannot detect below 125. But earth fault you can detect anywhere above 10 amperes. So that's why you need a separate earth fault relay, because it gives you a high sensitivity in the protection. Without that your sensitivity is not there. And most of the faults that we face in the real life have a high percentage of earth fault. Okay, this is another example system which is worked out in this thing. We'll quickly have a look at it. Star grounded, transformer, another cable, then another 11 kV system and a source, and we are trying to coordinate the earth faults of these two. It's told to you that here there is a normal inverse plus a instantaneous characteristic which is available, and here you have only a normal system inverse characteristic. The CT ratios are 500:5 for normal inverse, 200:5 for the one of the two. I mean, I'm not very sure which one, but 500:5 probably for the instantaneous and 200:5 for normal inverse or whatever. And this one is 200:5 for here. That's because the current in the high voltage side, fault current is here. The fault current seen here will tend to anyway reduce. Okay. Now I want to coordinate. One thing is setting up of instantaneous relay of R1. That is not a major problem. You look at the fault current, since there is no backup responsibility for R1 here, you can easily set up the instantaneous element here. That's not a major thing. Then there is a normal inverse characteristic that you would set up to 0.1 seconds, for example. So there is something else, maybe a fuse here down the line which I have not shown, and therefore normal inverse is more or less straightforward for this particular example. Then there is a normal inverse, instantaneous is more or less straightforward. Normal inverse would be set up with a minimum time multiplier setting of 0.1. So that's what you would do. And okay, so the fault currents are given here. SLG fault current at bus A is 480 amperes and bus B it is 650 amperes. So 480 amperes and 650 amperes. These are the fault currents. Compute the time required for R2 to clear SLG fault. Coordination time relay interval is this. Maximum system unbalance is 20%. So what I do here, setting of R1, choose the pickup value of R1 about 20% of the full load current because unbalance is 20%. Calculate instantaneous relay pickup value. Since R1 has no backup relay, TMS should be set to its minimum value. For fault current of 480 is calculated. Time of operation of relay is found out from the standard inverse characteristic. So that's what, the standard steps were followed to find out the time of operation of the relay at TMS of 0.1. Then to that you added a coordination interval of 0.3 and you got the TMS value of 0.739 for this. Now what is the pickup here for relay R2? Setting of relay R2 has to provide backup to the bus A. Time of operation of R2 has to be time of operation of R1 plus CTI. Since this relay is on the primary side of the transformer, all calculations are done with respect to the primary side of the transformer. Choose pickup current about 20% of the full load of primary side. For the corresponding fault current on the primary side, PSM is calculated, now TMS, etc., etc. So what I am saying here is, one thing you just look on the x-axis. The fault current is all referred to primary side. So because I am doing coordination and this is doing a protection on the secondary side, this is doing a protection on the primary side. A transformer may have a differential protection, for example, not typically because it's a small device, it has a differential protection. Transformer also requires protection, but it is usually the differential protection that I said. Primary protection of a fault in transformer is differential. So this coordinates transformer plus all this here, and the currents are given, impedances are not required because currents are already given to you. So what 144 here means the 450 amperes which is referred to the primary side. To draw this coordination curve, all the currents should either be referred to the primary, or all the currents, when there is a transformer in between, all the currents should either be referred to primary or they should be referred to secondary. So we have referred all the currents to the primary side. That's why this 450 amperes is shown as 480 amperes is shown as 144 amperes here. And then we have added 0.3 seconds, and then with that 0.3 seconds we have calculated what is the time dial setting of this relay, and then from there for its maximum fault current here, what 650 amperes, what is the operating time. So the philosophy is more or less similar. Okay. I think a quick note on adaptive relaying. Basically, system conditions change throughout the day, load conditions change throughout the day. So if you want to make your protection more effective than giving a one setting for a whole day or a whole year or whatever, you could actually have with a computer relay a lookup table, and according to the changing systems or times or so on, or feeders in service, not in service, you could change the pickup setting by through a lookup table. So that is a simple idea of adaptive protection in this particular sense, that you don't try to give one setting for all kinds of things. Try to give settings which depend upon which circuits, feeders are in service, or loading conditions, or time of the day, and that can give you a more sensitive protection than one single setting. So that's the notion of adaptive this thing. And a quick touch on the automatic reclosers. As I said, most of the faults are temporary faults, they are not permanent faults. So therefore what happens is, when you clear, first time you clear it, you instead of taking, you can wait for a few cycles and then reclose, and if it is a temporary fault, few cycles wait for deionization of the arc, that is the fault is quenched, and then try to close again, automatically go for a reclose action without ascertaining whether it is a permanent fault or not. If it is not a permanent fault, then what would happen, you reclose it. If the fault has cleared, the system will continue to work in its normal way. If the fault is still persisting, then again you would open out, the circuit breaker will again trip, then again you will give a dead time for the arcs to deionize and so on, and then again close it, and then again the circuit breaker, if the fault persists, then like this you would go through 3 or 4 dead time intervals, after which the fault will be declared as a permanent fault and the system will go for a permanent trip. So many of you may have seen this happening also at least in our hometown. We always used to see, say that, if it goes, then it will come after a long time. Otherwise it comes back more or less very quickly. Once or twice it comes back quickly, and then after that it's gone. Means there's a recloser somewhere which is trying to work it out. If it is a temporary fault, the recloser would succeed and system will continue as it is. So reclosers are designed with the idea that most of the faults are temporary in nature, and they could be single phase reclosers or 3 phase reclosers. That both of it is possible. They also have a voltage rating, continuous current rating, and these are the standard some of the ratings that you have. And cable faults, underground cables, if you have in a system, they are always having faults on underground cable systems are always permanent in nature, more or less. Rather, with the overhead system, overhead transmission, the faults are more predominantly temporary in nature. With the underground system, any fault on a cable is more of a permanent fault in the system. So recloser action is not recommended if you have cables in the if you have underground cables in the system. Recloser action is only meant for faults on an overhead system. Recloser action is not meant for, and if you have a mixed system with overhead and underground, then, and if you want to use recloser, then you need more refined schemes to decide whether the fault is on the overhead section or on the cable section before the recloser action is to supervise the recloser action. Okay, so we'll stop here for today.